This is my first lab report for Physics 2211 regarding the movement of an object with constant velocity and zero net force. The purpose of this experiment is to study the position of an object with constant velocity and make predictions using Newton's second law, which is interesting because the constant velocity allows one to predict position. This is demonstrated through the two equations showing the change in velocity and position on the right. One can see that if F net is 0, Vf is equal to Vi, which can immediately be plugged in to the position formula. I chose a rolling ball for the system because if it's measured quickly enough, it appears not to accelerate. The results of this lab showed the model was a poor fit for the ball's position as the lines representing the two positions diverged, but this may have been due to a poor setup. To begin the experiment, I used a blue lacrosse ball to describe translation across a single plane, which was my deck in this case. I filmed the video, then uploaded it to Tracker, which I used to keep track of my movement observations. Additionally, I used GlowScript and the base code given to model the predicted movement of the lacrosse ball if there were truly no net force. Finally, I compared the two sets of data by putting it into a line graph. Some assumptions I made. I assumed the F-net was 0. I assumed that my deck served as a flat plane, and I assumed some even time frames, which may not actually apply to the ball since these conditions are hard to meet in the real world. I also set it up so that my lacrosse ball was rolling from right to left. After filming the video and uploading it into Tracker, I edited the frames to start at 155 so the ball would already be in motion without the initial acceleration, and ended at 210 when the ball went off the screen. Let's watch my video now. So the initial velocity was calculated using the first two data entries, and the initial position was measured in Tracker. This was only slightly off-center of the origin at 0.09116, 0, 0. I set a calibration stick by fitting it to a meter stick I had in the video. Then I set the axes so the ball would move in the positive x direction. Finally, I tracked the point mass in Tracker manually after starting it at the center in frame 155. The video shows my video and the model that Tracker created for me manually clicking in the point mass. We can see that the model resembles a positive linear line, which indicates a constant velocity since there was no speed or direction change. While using GlowScript, I edited the initial position to be what it said on frame 155 since it was assumed to be 0 in the original code. I also edited the initial velocity using the first two data entry points in Tracker, and it came out to be 1.69 meters per second. I edited the delta t in GlowScript to be 0.033 since that was the delta t in Tracker. I wanted the predicted positions to match the observed, so I also edited the while loop to match the cutoff time of 1.8 seconds in the video as well. F-net was also changed to be 0 since we were assuming an F-net of 0 for this project, and I also updated the equations for velocity and position to fit Newton's second law from the original code, as seen in the bottom right. Here is the comparison of the predicted and observed positions with the observed in blue and the predicted in red. It appears to fit almost exactly at the beginning, but the observed position tapers off from the predicted at the end, making it a somewhat ill-fitted model. This could be due to friction from my deck acting on the ball. This would make sense as the predicted position is more than the observed, since the predicted model ignores other forces, which are impossible to ignore in the real world. I could have measured the ball over a smaller time frame, which would mitigate the effects of other forces acting upon it over time. This would be effectively cutting off the graph as seen here, and this implies that there was not an F-net of 0 for the observed movement, which means there was not a constant velocity for the lacrosse ball. So what would happen if the x-axis were to be flipped? In this video, the ball rolls from the left side of the screen to the right, which mirrors the normal Cartesian x-plane, which goes from the negative side on the left to the positive as the line continues to the right. If I were to roll the object from right to left, then the measured velocity would be negative, since the position would go from being positive to negative as time continued. The magnitude would remain the same, but it would be in the opposite direction. This property comes from velocity's designation as a vector, which gives it magnitude and direction. In the event that the x-axis were to be flipped, only the direction would be altered, which results in a different velocity but the same magnitude. What would happen if F-net was not 0? So since F-net is equal to 0, this means that the object travels at a constant velocity, experiencing no change in direction or speed. When F-net is not 0, objects experience changes in acceleration, meaning that the objects will not travel at a constant velocity, as is the case for my observed motion as the velocity tapers off towards the end. In the case of the predicted model, the gravity pushes down on the ball, Earth pushes back up with normal force. My applied force also pushes against the force of friction with the deck. These four forces sum to 0, giving the ball an F-net of 0. For my observed case, the F-net did not quite sum to 0, as discussed with the tapering off of the positions at the end, but it still has normal force, gravity, applied force, and friction working on it, but it did not result in an F-net of 0 in this case. Thank you for listening to my report.